Hello, everyone. So we'll get started. Welcome to this webinar titled Demonstration of Altair Feko for Antenna Simulations. This webinar is sponsored by a few IEEE groups, including the IEEE Ottawa and Montreal sections, Ottawa Young Professionals, and Ottawa and Montreal Antennas and Propagation chapters. Leading this webinar is Gopinath Gampala, who is the manager of the global technical team with Altair. He holds bachelor and master's degrees in electronics and communications engineering, and he has more than 15 years of experience in the field of computer-aided engineering. Gopi, thank you so much for being with us. Over to you.
Thank you. Let me share my screen. Can you see my screen?
Yes.
Okay. Hello, everyone. As I was just introduced, my name is Gopi Gampala. I work with Altair, but I'm also associated with IEEE from a long time, and I'm a senior member with IEEE. So today's talk, it's mostly about the demonstration of Altair Feko for antenna design. Altair Feko, it's a high-frequency 3D electromagnetic simulation software. But just like a couple of weeks back, there was another talk given by Dr. C.J. Reddy. And today's talk, it's kind of a continuation of the previous talk. The previous talk was focusing on the different modeling and simulation techniques available within Altair for high-frequency electromagnetic solutions. So following that, today we'll focus mostly on the application side with some live demonstrations. So this is the outline for today's talk. We'll briefly go over the high-frequency EM simulation tools within Altair, and followed by a brief overview of Feko, which is the main topic for today's discussion. And when it comes to the live demonstrations, I would like to focus on a few different topics. One is antenna design, of course, but we can also look into antenna arrays as well as the antenna design optimization. Okay? And then we can look into some of the student resources that are available within Altair. So coming to the high-frequency electromagnetic simulation tools within Altair, there are a few of them. And Feko is, of course, the primary one. All the other ones follows under the broad umbrella of Feko, but they are also dedicated tools on their own. The other two ones are Altair WinProp as well as RAP. WinProp, it can be used for wireless coverage as well as network planning, meaning so when you use Feko, you can design antennas or antenna arrays, right? But if you want to test your antennas within their working environment, whether it is an indoor environment inside a house or an office building, or whether it is an outdoor environment like in a city landscape, so you can use WinProp for the coverage of your antennas, as well as do some network analysis for some specific technologies. Like if the application is for LTE or 5G, then you can look into the data rates or throughputs or the reference signal outputs, SNR levels, all those for the given technology. Yeah. So not stopping there, if you also want to manage the spectrum for different applications, depending on what are the different frequency bands available, which of them are free and which of them might interfere depending on if they are adjacent to each other. So you can do spectrum management using RAP, as well as for other applications like coverage of satellites or radar coverage. Okay. So Feko combined with WinProp and RAP, it covers a broad range of high frequency EM applications. So if we look at all those different applications, of course, antenna design is one of the primary applications, but not stopping at antenna design. So when you design an antenna by itself, it can have excellent impedance and radiation characteristics. But when you integrate the antenna in its working environment, then the in situ analysis is as important as the antenna design itself. Okay, so because of the surrounding environment, there might be a frequency shift, the radiation pattern shape might change. So antenna placement is another primary application of Feko. But as I said, Feko combined with WinProp and RAP, it covers a broad range of applications. Like you can do a virtual drive test or a virtual flight test. You can use Feko for EMCMI applications, especially covering both the radiated emissions as well as the susceptibility analysis. It can be used for scattering analysis or for bioelectromagnetic applications, designing MRI coils or calculating the effect of high intensity radiation on human phantoms, like specific absorption rate calculations or radiation hazard analysis. It can also be used for designing microwave components like filters or like power dividers. It can be used for designing radomes as well. So a broad range of applications. Okay. So one of the primary reasons why a single tool can be used for so many different applications is uh, the availability of many different solvers. So let's look into an overview of Feko by itself to get some understanding of what are the different solver technologies available and where they are applicable or where they are primarily used. Yeah. So coming to Feko, it's high frequency 3D electromagnetic simulation software, primarily focused on frequency domain techniques, but it also offers a time domain analysis in the form of finite difference time domain. And as we just saw, it can be used for many different applications. So coming to the solvers in Feko, Feko is based on method of performance, meaning when a user does not specify any particular solver in Feko, method of performance is used by default. But apart from method of performance, as you can see here, it also offers a finite element method, a finite difference time domain, adaptive cross approximation, multi-level fast multipole method, physical optics, ray launching geometrical optics, as well as uniform theory of diffraction. Okay. So because all these solvers are integrated or available within a single tool, that is the reason it can be used for a broad range of applications. If you look at the bottom ones, like a finite element method all the way to multi-level fast multiple method, those are all categorized as full wave solvers, meaning we solve Maxwell's equations exactly without any approximations. The only approximation being the discretization or the meshing. Okay? And the top three, they are classified as the asymptotic solvers because they involve some high frequency approximations. Okay? But if you model the problem well within those approximations, you will get an answer which is very close to a full wave solution. When you use a full wave solution, because there are no approximations, that's the most accurate numerical solution you can get for a given problem. Okay? But using asymptotic solvers for a lot less computational resources, you will still be able to come close to a full wave solution, provided you are well within the approximations of that given solver. Okay. And the chart here, it can also be used as a guide to decide when to use which solver. So depending on the electrical size as well as the complexity of the given problem. Okay. So if you're dealing with electrically small structures, which are also complex, which need some fine discretization, then we would recommend to use finite element method or finite difference time domain, as well as method of methods. Okay. But if the problem is electrically small, but it has a dense mesh where method of means might take a lot of memory, and then you can use adaptive cross approximation, which solves the matrix equations in parts and still try to fit the problem within the available memory. As the problem becomes electrically large, meaning like multiple wavelengths in size, let's say more than 5 or 10 wavelengths in size, then the bottom solvers, they tend to take more memory and time. That's where MLFMEM comes into play, where it is like an acceleration of method of MEMS. So because of the acceleration or the inherent boxing algorithm for MLFMEM, it takes a lot less memory and time compared to method of MEMS. So you will be able to solve electrical large structures with a small and more amount of computational resources. Let's say you have a problem and you have fixed hardware resources. Okay, you don't have an option to change the hardware or go with a bigger machine to solve. Then if you can't solve the problem even with MLFMEM, the alternative is to go for these asymptotic solvers, so like physical optics or LGO or UTD, depending on the application type. Okay, because those involve some approximations, they are used for some specific applications. Apart from all those different solvers, there are also additional solver features within Feko, like being able to handle infinite ground planes or substrates, and also the option to add periodic boundary conditions, especially for solving problems like frequency selective surfaces or high impedance surfaces. And Feko also has built-in characteristic mode analysis. So if you want to just understand the natural behavior of a given geometry, irrespective of any excitation, then you can use CMA, characteristic mode analysis, which will give you the natural resonant mode, so depending on the frequency. Okay. And if you want to add some external circuits like some matching circuits or some complex feed networks along with your antenna or antenna arrays, then if you just have the network parameters like S parameters, Z parameters, or Y parameters, then you can use the non-radiating networks feature in Feko. And for automotive applications, for designing antennas integrated into windshield, we have the windscreen antenna feature. And for EMCMA applications, there is a fully featured cable analysis module integrated into Feko. And the best thing, especially for students, would be the availability of a component library, which is a library of some pre-designed antennas as well as some platforms. Okay, so if you don't want to spend time designing an antenna from scratch, you can use the component library and pick an antenna from the library depending on some keywords. Let's say you are looking for some broadband antennas or high gain antennas, then it can shortlist which of these antennas are suitable for these keywords. And once you pick an antenna from the library, you can specify the frequency as well as the solver that you want to use and add it to your Feko project. Okay, so when you add it to your Feko project, the model will be a fully parametric design, meaning it is designed using design variables. So you can obviously change the design by changing the values of the design variables. Or if you want to optimize the design or tweak the design for a different application, then you can also set up optimization with a fully parametric design and optimize the problem or the design for the new application. Okay. As I said, optimization is completely built or integrated into Feko, and there are several different optimization algorithms available within Feko. So we can go over them when we do a live demonstration. So apart from all those different solvers as well as solver features and optimization built into Feko, if you want to automate something, then that is also possible using Feko. Okay? So we have Lua scripting built into both the preprocessor as well as the post-processor of Feko, where everything that you can do from the graphical user interface, you will be able to do it from a script. Okay? So using the Lua scripting, you can automate everything that you can do either on the pre-processing side or on the post-processing side. So that was just a brief overview of Feko and its capabilities. Now, looking at Feko, primarily focusing on antenna design. So just a quick recap of all the different solvers available in Feko. So we have method of means, which is the default solver, but we also have finite element method, finite difference time domain, which are another two full solvers primarily used for antenna design. And we have MLFMM for electrical large structures, as well as physical optics, RLGO, and UTD, also for electrically large structures. Okay. Now, if you want to use a simulation tool like Feko, you don't need to know all the working principle or the theory behind all these different solvers, but some basic understanding of these solvers will definitely come in handy to decide which solver to use for which type of application. Okay, so if you look at the Fourier solvers, we have MOM, ACA, MLFMM, FEM, and FDTD. And if you look at the asymptotic solvers, there are physical optics, LEPO, which is large element physical optics, RLGO, which is also similar to shooting and bouncing ray method, and UTD. Okay? But not only having all these solvers in Feko, they are also hybridized, meaning you will be able to use multiple solvers within the same project. Okay? For example, method of means FEM and MLFMM, those are all hybridized. So within the same project, you can treat part of the geometry with method of means and a part of the geometry with FEM. Or if you want to use an asymptotic solver like physical optics or RLGO or UTD, all those asymptotic solvers, they are hybridized with method of means, and some of them are also hybridized with MLFMM. Okay? Especially physical optics and large element physical optics, they are hybridized with both method of means and MLFMM, whereas RLGO and UTD, those are hybridized with method of means. Okay, so what that hybridization brings to the table is, especially when using these asymptotic solvers, the source part or the primary antenna part can be treated with method of means or MLFMM, depending on the size of the source part. And the rest of the geometry, which would be electrical large, that can be treated with one of the asymptotic solvers. Okay? But for applications where FEM might be beneficial, especially for geometries which involve multiple dielectrics or inhomogeneous materials, there FEM and MOM or MLFM hybridization will come in handy. Okay? Or when treating problems like coupling between antennas which are separated by a distance, but the antennas by themselves are complex, which where FEM might be beneficial, then instead of enclosing both the antennas and the free space between them in an airbox, you can use the hybridization, where the exterior of the antenna can be treated with method of means and the interior of the antenna can be treated with FEM. This way, you don't need to discretize the free space between them. Okay? So this is how the hybridization can help to solve a given problem more efficiently, especially that can save both memory and time. Okay? Now, coming to the different types of antennas that can be handled with Feko. Obviously, Feko can treat wire antennas efficiently because of method of means and MLFM solvers in Feko. But not stopping there, you can solve both conformal as well as planar antennas, including dielectrics. And not stopping it just the antenna design, you can design antenna arrays. They can be either planar arrays or some 3D arbitrary arrays. And it can be used for designing other antennas like horn antennas or aperture antennas, dielectric lens antennas, or reflector antennas, as well as some antennas integrated into these complex handheld electronic devices. Okay, so depending on the complexity as well as the size of the antenna, you can use different solvers within Feko, which you can see we have listed the solvers that are suitable for the given type of antenna. And I don't want to take too much time focusing on the slides themselves. We can move on to the live demonstration. If you look at all these different types of antennas, there are like wire antennas, planar antennas, antenna arrays, and lens antennas, horns, right? So we can do one example for each type of antenna. That way we can learn the setup of that antenna as well as the results, like when you solve that kind of antennas, what type of results are available to plot in Feko. So before we look into the actual antenna examples, let me quickly give you an overview of the interface itself. Okay? When it comes to Feko, there are two primary interfaces. One is the pre-processing interface, which is CAD Feko, but there is also a post-processing interface to plot the results. Okay, once you set up a problem and solve it, and to plot the results, we can use the post-processing interface, which is post-Feko. Okay? Both of them have a similar layout, but we'll first look into CAD Feko. So when you install Feko, if you look into the installation start menu, so you will see a Feko launcher available as a part of the start menu. And under the Feko launcher, you can see all the different software that are installed using a single installation file. Okay? The single Feko installation file will install Feko, WinProp, as well as a new facade. RAP is a separate installation, but once you install it, it is also available under the same Feko launcher. Okay? And all the different tools like a CAD Feko, Post Feko, as well as the WinProp tools, the RAP tools, they are available in a single place to make it easy to access them. Okay? Now, when you open CAD Feko, this is what you see, where you have an option to start a new project, or if you're already working with Feko, then all the previously closed files, they're also available for a quick selection. And with the installation, the complete documentation or the user guide is available. It's part of the installation. But there are also a lot of examples that come with installation, and a complete detailed documentation of those examples is also available as part of the installation. Both the getting started guide as well as the example guide, those are the documentation for examples. And there are a couple of videos that come with installation. So if you're new to the software and you want to have some overview, you can also go through those videos. And under the Feko launcher, there is a documentation section. So you can access the documentation from the documentation section under the Feko launcher as well. Now, when you open or when you start a new project, let me click on Create New Project. This is how the interface will look like. On the top, you have a ribbon with the different contextual tabs. It's like Microsoft interface. I believe all of you are familiar with Microsoft because you might be using different tools like PowerPoint, Word, where you see a ribbon with the different contextual tabs. So Feko also has a similar interface. And the general workflow, when you are new to the software, I recommend following this workflow, but it's not mandatory. You can use it as you want. But typically, you start with the construct tab where you have all the features that are required to build a geometry, define materials, and assign those materials to the given geometry. Okay? So under media, you have all the different types of materials that you can define in Feko: metals, dielectrics, layered materials, anisotropic materials, impedance sheets. Feko can handle all of these materials. And you can model different wide structures, planar structures, 3D structures. There are some extend features like a spin, loft, sweep, path sweep. So these simple primitives in combination with these extend features, you can build some complex shapes or complex geometries within Feko. And under transform tab also, there are some features that can be used for building the geometry, like making multiple copies or translating, rotating, aligning, okay, all those capabilities. So between construct and transform tab, you have everything that you need to build the geometry that you want to solve. Okay? And then you move on to the source load tab, where you can specify the frequency, add ports and excitations, add loads if you want, or add some networks if you want, and then move on to the request tab to request for the output quantities that you want to solve for. Then mesh the model with respect to the highest frequency. Then go to the solver run tab and click on Feko solver to run the analysis. Okay? And once the simulation is done, you can go to post Feko to plot the results. Okay? So if I open post Feko, so you have the option to open the post processing interface directly from the Feko launcher, or you can open the post processing interface from CAD Feko itself. Once you are done with the simulation, you can open post Feko from CAD Feko also. Okay? And as I said, post Feko also has a similar interface like CAD Feko with a ribbon style and different contextual tabs. Okay? And in post Feko, you can plot 3D results as well as 2D results on different graphs, Cartesian graph, polar graph, as well as a Smith chart, or for quantities like radiation patterns. So you can also plot 2D surface plots. Yeah. Not only being able to plot the 3D and 2D results for certain types of 3D results like surface currents or electric and magnetic fields. You can also play animations where you can see how the currents or the fields are changing with respect to the phase. Yeah. And you can export those animations and include them in your presentations as well. Not stopping there, if you have multiple simulation models and you want to compare between them, you can load multiple models into a single post Feko session. Okay? So under add model, it will give you the option to load any number of models into the same session. And then you will be able to plot results from different models on the same graph. Okay? Not only that, let's say there is some external data. It can be data from some spreadsheets, or let's say you did some measurements and you want to compare the simulation data with the measured data. Then you can import the external data files also into post Feko and plot the data on the same graph along with your simulation data. Okay? Obviously, you can also export data from Feko to some external data files or some Feko specific formats if you want to use that, or if you want to import the data into some other tools for some external post processing. And as I said, the option to automate everything on the pre-processing side as well as the post-processing side, that is possible using the Lua scripting. Okay? So here you can see there is a script editor. This is in the post Feko. But if I go back to CAD Feko, also there is a script editor. Okay? The good thing with scripting or automation on the pre-processing side is if you are not familiar with Lua scripting, there is also an option to record. Let's say if I click on record and I start building my model, let's say I want to design or build a dipole antenna. Okay. So I go to construct tab. I always recommend to build parametric models. That way, if you want to optimize your design, it is easy to set up optimization because you need a parametric design to set up optimization. Okay. Let's say you create some variables. Okay. A variable a, the value of, let's say, 1, and let's say, and there is also a variable for frequency, and you want to solve, let's say, 300 E6. So I designed or I defined two different variables, and now I want to use those variables for designing my geometry. I start from, let's say, 0, 0, 0 to 0, 0, A, and I can call it anything I want for convenience. And then I can go to the source law tab and specify the frequency. So I can use the variable FREQ to specify the frequency, so which is 300 megahertz. Then I can, this is a wire, so I can add a wire port in the middle. Once we add ports, then we can add excitations to feed the antenna. So I can right click on that port to see what are the available excitations. And there is a voltage source that is available. Just for demonstration, we can leave the default values for magnitude and phase. I can add an excitation, and we can go to the request tab. Let's say I want to look at the 3D radiation pattern of this antenna. I can click on far field request under the request tab and request for 3D radiation pattern. Click on, there are shortcut buttons to request for 3D pattern or some cut planes. But if you want to request for far fields at any given direction, you can obviously do that by specifying the angles for both theta and phi, as well as the increment. So once we create an antenna, add a port and excitation to feed that antenna, and request for the output quantities that we want, I can then save this model, go to the Solve Run tab. So in Feko, automatic meshing is enabled by default. So as soon as I specify frequency, then the model is meshed with respect to that frequency. So I don't need to remesh again. But if I want to make changes to my mesh for some complex geometries, then I can obviously modify the mesh with respect to my own settings and remesh the model. Yeah. But by default, Feko has automatic meshing enabled. Now, if I click on Feko solver to run, then it will start running. So while it is running, let me come back to the home tab. Okay, it's already done. But if I come back to the home tab, and if I click on this record macro one more time, it will pop out the script that it recorded in the background for everything that I did, or for every operation that I performed. Okay. So I started by defining a couple of variables. So there is a variable A and there is a variable FREQ for frequency. And then I created a line for designing a dipole. And then I specified the frequency. Then I added a port. Then I added a voltage source. Then I added a request for the 3D radiation pattern. I saved it and I ran the application. Okay. Now to automate, let's say instead of solving this antenna at 300 megahertz, I want to solve it at 600 megahertz. Okay. So all I need to do is I simply change my frequency value to 600 and rerun the script. Okay. So let's say in the background, I start with an empty project. Okay. Now you can see there are no variables and no geometry in the 3D view. Okay. But if I run my script now, now you can see the variable is created, the frequency. Now you can see the new value, which is 600 megahertz. And there is the dipole. And if I look into the configuration, you can see the frequency, the port and excitation is added. The forward request is also added. Yeah. So this way, you don't need to like rebuild the structure from scratch. Yeah. Simply rerun the script with the modifications that are required, and it will automatically build that model for you. Okay. So that's the power of automation, and automation is built into Feko via Lua scripting. So let me close this. So that was a quick demonstration of the Feko interface, as well as the automation, the possibility of automation in Feko. And this is a dipole, which is a wire antenna. Now, let's say if I save it and run it, and open post Feko, now this is the post-processing interface where you can see the antenna that you solved, which is a wire dipole. And under add results, all the results that you requested for will be available for plotting in post Feko. And we requested for 3D radiation pattern, so that is available. So we can look at the 3D radiation pattern here. If you see this dipole, let me go back to CAD Feko quickly. The frequency is 600 megahertz, but the length of the dipole is 1 meter. Okay? But if you really want to design like a half-wave dipole to get like a donut shape pattern, you can make sure it is a half-wave wavelength at the operating frequency. So at 600 megahertz, the wavelength will be typically half a meter. So if you want to make a half wavelength dipole instead of 1 meter, you can make it 0.25. The wavelength is half meter, so half a wavelength would be 0.25 meter. Now, if you run it again, if you noticed, to change my design, I just updated the variable instead of going into the actual geometry and changing its specific dimensions. Okay, that is another advantage of building parametric models in a project. Now, if you come back to post Feko, so now you can see the donut shape pattern, which is expected of a half-wave dipole. Not only plotting the results in the 3D view, but if you want to plot them on a 2D graph, you can simply add a graph, which I clicked on polar, and empty graph is added. Now on this empty graph, I can plot the radiation pattern. So theta wrapped to get the complete cut plane, and check dB to look at the gain in dB. Yeah. So gain is a standard gain as per IEEE definition. But if you look at the realized gain, so this is the gain taking the mismatch into account. Yeah. Whenever you are comparing the simulation data with measurements, always compare the realized gain, because by default, the measurements will take into account the effects of mismatch. So you need to compare realized gain with the measured data. So not only gain, but Feko also can plot other output quantities like standard output quantities, so directivity, axial ratio, electric fields. So this is the radiation pattern. But if you want to look at the impedance characteristics of an antenna, you can plot them as well. If I click on Cartesian, once again an empty graph is added. Whenever you add an excitation in Feko, let me quickly go back to CAD Feko. So if you see here, under request, you have the option to request for far fields, near fields, surface currents, and you can request for S parameters. But you don't see an option to request for like input impedance or VSWR, those type of quantities, right? Why you don't have an option to request for them is, in fact, you don't need to request for them in Feko. Whenever you add an excitation, whether it is an voltage source or a current source, let me go back to the source load tab. So you have voltage source, current source, waveguide source, model source. Okay. For any excitation, whenever you add an excitation in Feko, source data is computed by default. Okay. That is why if I go back to post Feko, under source data, I can simply select that voltage source and all the source related quantities like reflection coefficient, VSWR, input impedance, input admittance, mismatch loss, power loss due to mismatch, source power. So those are all computed by default. Yeah, that is why there is no specific request in CAD Feko. Whenever you add an excitation, that itself is a request for all the source data. So when you look at the input impedance, you can look at just the real part. If I plot one more curve, I can change it to imaginary. So you can plot the real and imaginary part of the input impedance on the same graph. If I add one more graph, I can look at the reflection coefficient. Add one more graph, look at the VSWR. So we solved the model at a single frequency. That's why you see just a single point. But if I go back to CAD Feko and run this model over a frequency range, say I can change it from single frequency to, let's say, list of discrete points. Let's say I want to run it from 500 megahertz to 700 megahertz with some increment. I just simply specified some random increment of 10 megahertz. Click OK. And if I rerun it, so while the model is running, you can see the data being updated in post Feko. Okay. So this is the VSWR over the entire frequency range. And this is the reflection coefficient in linear scale. But if you want to look at the data in dB, once again, you can look at the data in dB. And this is the input impedance over the entire frequency range. So this is the radiation pattern. Because we ran over a frequency range, you have the option to plot the data at any specific frequency. Okay. Previously, it was just at a single frequency. But if you want to plot the maximum gain over the frequency, you can do that as well. Okay. So this is with respect to frequency. You can see how the gain is changing. So this way, in post Feko, you can plot all the different output quantities. You can plot the 3D radiation pattern, or you can plot the data in 2D on different types of graphs, polar graph or Cartesian graph, or even Smith chart. If I add a Smith chart, you can plot the source data on the Smith chart. So this is a quick demonstration to show the general use of the software or the general workflow to use the software. Okay. You start from CAD Feko. In CAD Feko, you can build your geometry, then add ports and excitations, specify the frequency, request for all the output quantities. Feko will automatically mesh the model with respect to the highest frequency, then run the analysis. Once you are finished running, open post Feko and plot all the different output quantities. If I come back to the slides, we have different types of antennas, right? Like wire antennas, planar antennas, antenna arrays, horn antennas. Okay, let's look at examples for these different types of antennas as well. Yeah. The first basic example for a half-wave dipole, obviously that is a wire antenna, but not stopping at just simple wires. If we have wires combined with some planar structures, Feko can handle them without any issues. So this is a helix antenna. So here you can see how the geometry is built. We have the helix primitive in Feko to build a helical antenna, and you can add ground plane using different surface options. And we have a port, and there is an excitation, voltage source excitation. And this model is ran from 700 megahertz to 1.3 gigahertz. Okay. So here we are looking at the 3D far field radiation pattern as well as the surface currents. Okay, if you want to look at the current distribution on this antenna, you can request for surface currents. So under the request tab, not only you can request for radiation pattern, if you want to look at the fields at any specific location or specific distance from the antenna, you can do that as well. So when it is a far field request, you are specifying the direction. So if I open the far field request, you can see the theta and phi angles, but you don't see the distance at which you are requesting for those fields. Okay? Because a far field request by default, the distance term is omitted, or the e to the power of j omega r by r, that term is excluded from the far field calculations. That is why for looking at quantities like gain or directivity, you use far field request. But if you want to look at the intensity of the fields at a specific distance from the antenna, then you can request for near fields. Okay? If I open the near field request, now you can request for fields at a specific distance in different coordinate systems, depending on the shape of the antenna and the distance or the area over which you want to look at the fields. You can use the Cartesian coordinate system, cylindrical with respect to different axes, spherical coordinates, or you can use the specified points option to just specify some specific points where you want to look at the field intensity. Or if you're using the finite element solver in Feko, then you can request the fields with respect to the mesh of the geometry itself. Okay. Now the currents, the request for looking at the current distribution on the antenna, that is also available. So under the request tab, you can simply request for the currents. If you go to post Feko, so this is the antenna that you can see in the post processing interface. So whenever you're looking in CAD Feko, it is the geometry or the CAD. Okay? But whenever you look at the model in post Feko, it is the mesh that you are looking in post Feko, not the CAD. Okay. But if the geometry looks like an exact representation of the CAD that you had in Feko, that means meshing wise or discretization wise, you did a good job to capture the exact shape of your geometry. Okay? So this was a helix, and we are able to capture the curvature of the helix accurately with the curvilinear segmentation on the wires. So that's why we can see an exact representation of the antenna with the mesh. Okay? Now, the surfaces, now you can see they are being discretized with triangles. So if you joined the first talk that was given by Dr. C.J. Reddy a couple of weeks back, you would have looked into different solvers, theory behind those solvers, and the type of mesh that is being used for all those different solvers. Okay? With method of means, surfaces are always discretized into triangles, and wires are discretized into segments with certain radius. So that's the meshing you see on this helical antenna. Now, if you look at the 3D radiation pattern, so you can see this is the gain pattern. So if you want, I can plot these output quantities one more time. So you can check dB. And if you want to hide that grid, you can go to the result tab and hide the grid for better visualization. If you want to look at the 3D geometry along with the radiation pattern, if you want to make the radiation pattern slightly transparent just for visualization, now you can also change the opacity. This way, you can look at the geometry as well as the radiation pattern. Now let me hide that radiation pattern. If you want to look at the surface currents, you can request for the surface currents on the ground plane, or you can request for surface currents on the helix. Now, when you're looking at surface currents, let's say you want to play animation to see how the currents are changing with respect to the phase. So I can change the type to phase and play animation to see how the currents are changing. Or let's say you want to look at the direction of the currents, you can go and you can show arrows. And then you can play again to see how the currents are changing or the direction of the current is changing with respect to the phase. If I look at the currents on the ground plane in dB, maybe we can look at the direction of the current flow better. So let me play again. Now you can see the currents on the ground plane better. So this is the helical wire antenna, and we are able to look at the surface current distribution as well as how the currents are changing with respect to the phase, as well as plotting the 3D radiation pattern. Okay. Now moving on to the other type of antennas. Now instead of wire antennas, so let's say we can move on to the planar antennas. So this is a planar microstrip antenna where we have a ground plane and we have a substrate and we have a square patch. Okay. The substrate being modeled using the cuboid geometry primitive, but depending on the shape of the substrate, if it is a conformal antenna, you can use different geometry shapes, use the sweep and path sweep options to create conformal geometries. Yeah. And for materials, the previous helical antenna, it was all metallic, but here this is a microstrip patch antenna. So this is an antenna patch on a dielectric substrate. So you can create dielectric materials in Feko. So under the media drop-down menu, you can see the option to define or create different types of materials. So if I open the existing material in this design, so this is a dielectric substrate with a dielectric constant of 2. When it comes to Feko handling different types of materials, these materials, they can be frequency independent or they can be frequency dependent. Yeah? And if you know the coefficients for any of these methods, you can define frequency dependent materials as well. Yeah? And if you look at the results for the microstrip patch antenna, so once again, we can see this is the geometry shape. So here we can look at the 3D radiation pattern as well as the surface currents. Okay? So if you want to look at how the currents are changing with respect to the phase, you can see, but maybe it's better with the arrows. So you can see how the currents are changing. And this is the radiation pattern in the two principal cut planes, phi is equal to 0 as well as phi is equal to 90. Okay. As I mentioned in the beginning, when you don't specify to use anything in Feko, Feko will use method of means by default. But Feko also has many different types of other solvers like finite element method, finite difference time domain, MLFMEM, right? Let's look into a patch antenna example, which is solved using finite element method. By default, finite element method in Feko is hybridized with method of moments. Yeah? So if you want to use hybridization, you don't need the airbox. You can just have the antenna. Okay? So this is a rectangular substrate, and we have a rectangular patch. Okay? But so when you use the default hybridization, what happens is the exterior most surfaces, they will be first solved with method of moments, and then that method of moments solution will act as a boundary condition for the interior volume, which will be solved with finite element method. But instead of hybridization, if you want to use pure FEM, that is also possible. But to solve an antenna model with pure FEM, you need to enclose the antenna in an airbox. Okay? And that is what we did here. Okay? So you can see the antenna, and we can see the larger airbox enclosing the antenna. Okay? And the way FEM is specified in Feko, you select all the regions, you go to properties, and under the solution method, let me open the previous example here. So you go to regions, you go to properties, and under the solution method, instead of the default method of methods, you can change it to finite element method. Okay? And when you change it to finite element method in here, it is still going to be FEM hybridized with method of methods. So after changing the solution method under the regions, one additional step you need to do is go to the solver tab, click on solver settings, and here under the FEM tab, enable the option to decouple from method of methods. When you decouple from method of methods, now the airbox will be terminated with absorbing boundary conditions. Okay? So without decoupling, the exterior most surfaces will be first solved with method of methods. That will act as the boundary for the FEM. When you decouple, then by default, Feko will use the absorbing boundary conditions on the exterior airbox, and then it will be solved just with FEM. Okay. Now, if you look at the results, okay. So here, this is the patch antenna with an airbox, and we can look at the reflection coefficient. But the same antenna, we can also solve with FDTD. Okay. The way you can enable to use FDTD is simply going to the solver tab, clicking on solver settings. Under the FDTD tab, activate finite difference time domain solver. Even though FDTD will also need an airbox, just like FEM, you don't need to manually create that airbox like FEM in Feko. When you activate FDTD in Feko, automatically that airbox will be added, enclosing the antenna, and you have the option to control the FDTD boundary conditions, whether you want to use the open boundaries, which is like a PLM, or if you want to use PEC or PMC boundaries. Okay. Because this is a radiating structure and antenna, we are just using open boundaries in all directions. Okay. When you solve this same antenna with two different solvers in Feko, you can also do cross validation. So that is another advantage of having multiple solvers within the same tool. Okay. Feko having multiple solvers, it can be used for cross validation. You solve the antenna with FEM, you solve the antenna with FDTD, and you can plot the results on the same graph. You can see the resonance is at the same frequency. And even if you look at the radiation patterns, okay. So this is the first one is phi is equal to 90. So let me change the result for FDTD to phi is equal to 90. And once again, you can see there is a pretty good agreement between FEM and FDTD. So this way, even before doing measurements or anything else, you can test the accuracy of your simulation by solving the same problem with two different solvers in Feko and comparing between them. So this is the patch antenna solved with both FEM as well as FDTD. Now, if you look at the other types of antennas, like horn antennas, once again, we can look at those type of antennas. So for horn antennas, there are different types of antennas. It can be like pyramidal horns or Potter horns. So this is an example of a cylindrical Potter horn. So when you model horn antennas in Feko, instead of wire ports or other types of ports, we also have waveguide ports, where with waveguide excitations, you have the option to specify the modes manually. Yeah. Whatever mode you want to excite on that given waveguide, whether it is a T mode or TM modes, or if you want to excite multiple modes at the same time. So Feko gives you the option to specify multiple modes. Yeah. Or if it is a coax, you can specify TM modes on it. So these type of horns, they are typically used as a feed for reflector antennas. But if you look at the radiation pattern of just this antenna by itself, so you can see this is the Potter horn, and it's a 3D radiation pattern. Not stopping it, just designing the horn antenna by themselves, you can design reflector antennas also using Feko. Let's look at some examples of reflector antennas. So this is an offset reflector. So where you see the reflector as well as the feed at an offset. And here, whenever you're solving antennas like reflector antennas, because of the size of the reflector, which typically will be multiple wavelengths in size. So instead of using the default method of MEMS, we would recommend to use the solvers like MLFMEM. If MLFMEM is taking a lot of memory and time, then you can use the asymptotic methods like physical optics or ray launching geometrical optics. Okay. This is a reflector, offset reflector, which is solved with both MLFMEM and physical optics. Now, if you want to switch from default method of movements to MLFMEM, it's very easy to switch. All you need to do is go to the solver on tab, click on solver settings, and under the MLFMEM tab, just enable MLFMM. That's all. Okay. Everything will be solved with MLFMM instead of method of movements. So it's very easy to switch between method of movements and MLFMM. Okay. But to specify any of the asymptotic method, whether it is physical optics or RLGO or UTD, you do it on the geometry level. So you select the geometry surface. In the detail section, you can look at the surface, go to properties, and under the solution tab, you can specify which asymptotic method you want to use on that particular surface. Okay. So you can use only one of the asymptotic method in combination with method of movements or MLFMM. You cannot use multiple asymptotic methods within the same project. So it can be physical optics with method of movements, large element physical optics with method of movements, RLGO with method of movements, or UTD with method of movements. So here on this reflector, we specify to use physical optics. Now, if you look at the results, so this is the offset reflector treated with MLFMM, and this is the offset reflector treated with physical optics. Okay. Here, the source part, which is the horn, is treated with method of MEMS, but the reflector part is treated with physical optics. Okay, that is what we just saw in CAD Feko. Okay, on the reflector, we specified physical optics, but the source part, which is the horn, it is all treated with method of MEMS. Okay, if I go back to post Feko, MLFMM being a full wave solver, it solves Maxwell's equations exactly right. So that is an accurate numerical solution. So we can compare the asymptotic method, physical optics, which involves some approximations, with MLFMM to test the accuracy of the asymptotic method. Now on this polar graph, let me close it, plot it one more time, just for demonstration. So I can plot the results. So these are the results from MLFMM, offset reflector, MLFMM, and I can plot the results from physical optics also, offset reflector with method of MEMS and physical optics hybridization. Now you can see here, the results are pretty close to each other. Okay, not a big difference between the full wave MLFMM solution as well as the asymptotic physical optics solution. But if you look at the computational resources, you can also open the output file. After every simulation, there will be an output file, which is an ASCII file, where you can open and you can read the contents of it, which will have the Feko version written to it, the number of cores used, as well as the number of mesh elements, everything. So all the data is written to the out file, including summary of computational resources. So here, the total time required with MLFMM is 66 seconds, and the total memory required is 1 gigabyte. But if you look into physical optics, the total time required is 42 seconds, and the total memory required is only 300 megabytes. Okay, you can see a clear savings in both memory and time when you switch from a full wave solver to an asymptotic solver. Okay? Here, this is not a big problem, but if you are solving a big problem, which is, let's say, multiples of tens of wavelength or hundreds of wavelengths in size, a problem that may take hundreds of gigs with MLFMM may take only few gigs with an asymptotic solution, or even few megabytes with an asymptotic solution. Okay? That would be the advantage of asymptotic solvers. And when you look at the accuracy, as we just saw, you are not losing much when you are comparing the results between a full wave solution and an asymptotic solution. Okay, so here we are comparing the results mostly in the visible direction. That's why you don't see a big difference. But the back lobes, there you might see some difference. But mostly for reflector type of antennas, you are interested in what is happening off of the reflector than what is happening behind the reflector. So you already know when you are using an asymptotic solver that there will be some discrepancies in the back lobe. So if you are okay with that, if you are interested in the main result, then we can save a lot of resources both in terms of memory and time by using an asymptotic solver in Feko. So this is physical optics, but let's say you're having dielectrics and you want to take into account the transmission through the dielectrics as well. For that, physical optics will have some limitation, as explained by Dr. Reddy in the previous session. Whereas RLGO, it can take into account the transmission through the dielectrics. For that reason, for problems like radomes or dielectric lens, so we recommend to use RLGO for handling electrical large dielectric lens or radome type of analysis. Yeah. So this is a dielectric lens, and here you can see RLGO is specified on this lens. So if you select both the surfaces making the lens, go to properties, solution, you can see RLGO is specified. Now, if you compare the results between MLFMM and RLGO, so here, this is a dielectric lens treated with MLFMM, and the next one is RLGO treated with RLGO. For the source part, instead of having the physical horn, we replaced it with an equivalent source. So here, under the solver and tab in CAD Feko, you can see you have an option to import either the near field data, the spherical mode data, or the far field source data in place of the physical antenna. Okay, so you can import. So you can import the far field data, the near field data, or the spherical mode data, and use it as a source in place of a physical antenna. For example, you don't have the physical design, but you got the data from some measurements or from some spreadsheets, then you can still represent that antenna in Feko simulations by using this equivalent source option. Now, if you compare the results, so here this is the difference between MLFMM and RLGO, and phi is equal to 0 cut plane. and this is in the other orthogonal cut plane. Okay, so in both the cut planes, in the main lobe, you can see they're pretty close to each other. Obviously, in the side lobes and back lobes, you might see some discrepancies, but which are expected because of the inherent approximations. But if you look at the resources, MLFMM took more than 300 seconds and more than 8 gigs of RAM, actually close to 9 gigs, whereas RLGO took only 4 seconds and like 25 megabytes. Okay, you can see orders of magnitude difference in the memory and time when you are switching to an asymptotic solver. Okay? So that is the advantage of these asymptotic solvers, where you can save a lot of memory and time, but not losing a lot in terms of accuracy. Okay? So not stopping at these just antennas. Let's say you want to solve antenna arrays. Okay. Now there are different options in Feko for solving antenna arrays. You can obviously model the whole array physically by replicating each element, adding excitations and specifying the phase difference between different elements. Or you can use the array tool in Feko. Okay? So when you use the array tool in Feko, so under the construct tab, you have the array tool for designing planar arrays, cylindrical or circular arrays, as well as some custom arrays. So here, this is a planar array. So when you use the planar array option, you can specify the number of elements in each direction, as well as if you want to specify some phase offset between different excitations, you can. But here I just went with some uniform distribution. Okay. So this is one option where you can use the array tool in Feko. The other option is modeling the entire array and solving with different solvers in Feko, depending on the complexity of each individual element as well as the overall electrical size of the array. Okay. So for this dipole array, if we look at the entire radiation pattern, so this is the single element. So this is with the finite array tool, and this is the finite array solved with method of Mintz. And this is the finite array solved with MLFMM. And this is the finite array solved with the finite element method. And the finite array solved with finite difference time domain solver in Feko. Now, when you're comparing all those different solvers, you can see the full wave solvers, MLFMM, FEM, FDTD, method of Mintz, they're all pretty close to each other. You can see the results are mostly agreeing well, including the array tool. Okay? But in Feko, there is also an option to use periodic boundary conditions. Okay, when you use just a single element, you can define a periodic boundary. And when you define a periodic boundary in Feko for any element, in fact, let's say if I go to CAD Feko and to open any element, when you request for the far fields under the advanced tab, you have the option to calculate the array pattern for a specific array layout. So here you can specify the number of elements along both the axes to define the entire planar array or the rectangular array, and then you can calculate the array pattern. Okay, that was the option used to calculate the array pattern for this single dipole. Obviously, there are some discrepancies when you are using the periodic boundary conditions, but it will be a quick calculation. Whereas modeling the array physically with all the elements, it will be more time consuming and it requires more memory depending on which solver and the overall electrical size. Okay. So this is a comparison between different options for arrays as well as the accuracy between them. So if you look at the microstrip antenna, which was solved with method of Mintz, and if you want to create an array out of it, we did that. And here we solved that microstrip patch array. And you can look at the complete array pattern. So this is the array model physically without using any array tool or anything else. Here we have the complete mounting structure as well as all the elements of the array, and you can plot the complete array pattern and both the cut planes. If you look at the memory requirements, so this particular problem requires a few gigs and solved at certain time, but this was solved with MLFMM in Feko. Okay, so maybe not here. Let me quickly go to the slides so that we won't waste time. So this array, if you are solving with method of means, it will require, because of the size of the array, it will require a lot of memory, more than 100 gigs of RAM. But instead, if you switch to MLFMM, as I just showed, if I go all the way to the end, it required less than 15 gigs of RAM. Okay? So that is the advantage of using MLFMM on electrically large structures. Okay? Both method of means and MLFMM, they should be as accurate as each other because they both are full use solvers. Okay. And the last topic was optimization. Without taking a lot of time, let me quickly show like optimization setup in Feko. So if you have a fully parametric design, so then you can set up optimization where you can add the optimization parameters with the range and define an optimization goal. So here we are trying to optimize this particular bent dipole in front of a reflector and maximize the gain in the azimuth plane or the XY plane. Okay? So when you set up optimization, you typically, what you do is under the solver and tab, unlike all the other problems where you click on Feko solver, you click on opt Feko to run optimization. And once optimization is finished, in post Feko, you can plot different optimization output data. Like you can see, okay, so with respect to every iteration of the optimization, how the parametric variable angle is changing, or how another parametric variable distance is also changing, as well as how the actual output quantity, which is the gain in the azimuth plane, how it is changing with each iteration. Okay, so after 15 or so iterations, you can see the line is staying more or less flat. Then the optimizer converged and it stopped. Okay. I think we have 10 more minutes left. I don't want to spend more time explaining how to set up optimization because I want to leave at least 10 minutes for Q&A. So are there any questions that I can answer?
Thanks a lot, Gopi. Thanks for the talk. It's really amazing. We start by the question. I think CG answered a majority of the question, but
yeah, just as a comment, Gopi, I think there was an active audience here asking a lot of questions, so I answered most of them.
Thanks a lot.
The talk. There's a last question, I guess, which I did not to answer. Maybe you can answer this. How do we know the used mesh is the best for our geometry?
Okay, so when you use Feko, as I said, if there is a frequency range, by default, Feko takes into account the material properties as well as the highest frequency into account and comes up with a mesh. Okay? So I would say like more than 90% of the times that should be good enough. But if you still want to do a study where you want to test if the mesh is whatever the default mesh you have is the right one or not, there is something called adaptive mesh refinement in Feko. Okay? So if you, instead of running the Feko solver, if you run AMR Feko, adaptive mesh refinement Feko, it will go through different iterations where in the first iteration, it will run and look for error estimates. Let's say if you're taking method of means, the solution is surface currents, right? Then it will look for the surface currents between the adjacent elements. and the gradient, basically the difference in the current distribution between the adjacent elements. And we don't expect a lot of variation between the adjacent elements. And if there is a lot of variation, that means the delta is more. So there, it assumes that the error is more. And in the other areas where the gradient is less, it assumes the variation is less and the results are accurate. And in the areas where the error is high, it will automatically add mesh refinements to refine the mesh and rerun the problem. So this iterative process will go on for few iterations. And when the result is not changing with additional refinements, it thinks that, okay, this is the most accurate mesh because the result is not changing with mesh or with any added refinements. It will stop and it will give you the answer. Okay? So if you compare a model where you start with a coarse mesh instead of using the default mesh in Feko, go through the refinements and use a model where you just take into account the material properties, the highest frequency, and the default mesh of Feko and compare the results. More or less, you will see that for majority of the cases, you will end up with the same answer. But just for testing, you also have the adaptive mesh refinement in Feko if you want to go through that iterative process. Any other questions, Dr. Reddy?
No, that was the last question, I guess, so that I see on the.
Okay.
I think there are more questions coming up. I think there's a question. If I want to make my probe radius large, like 0.6 millimeters, it shows the error, the ratio of the wire radius to length is too high. Then how can we think to modify the mesh? What type of calculation we need to put while using mesh?
Okay. So whenever you have wires in Feko, wires are treated with a thin wire approximation. By that approximation, we need the segment. So there is a simple correlation between the wire segment radius and the wire segment length. Okay, so the segment length should be at least greater than 3 times the segment radius. Okay? So whenever this rule is violated, let's say you have short segments and a high radius, that's where you see that kind of errors or warnings that the segmentation rules are violated. In those cases, if you're okay reducing the wire radius, you can. If you go to mesh and modify mesh, so there is an option to change the wire radius manually. Or let's say by requirement, that is the radius you want to use, because if you fabricate that antenna in real life, so that is going to be the feed pin radius, so you cannot reduce the radius. Then instead of modeling it as a wire, you need to model it as a cylinder. Okay? So when you model it as a cylinder, obviously it will be meshed into triangles or tetrahedrals depending on which solver you are using. And on the cylinder, you can use either the edge port, or if you model a full coax, you can use the waveguide ports or the FEM model ports. Yeah. But you have two options. If you want to go with the thin wire approximation, reduce the radius, or if you don't want to compromise on the radius, replace the wire with cylinder. If there are no further questions, I just want to point out that there is a Feko student edition. The name is just student edition, but it is no different from the full commercial version of Feko. Okay? So there are no limits on the student version that you can access. But to access the student version, you need to be registered on Altair.com as a student, and then you can get a license to work with. So please try to take advantage of the no limits Feko student edition and use it for your projects. And if you have any questions, there is also an active Altair community where you can post your questions. Other Feko users can answer your questions. Sometimes we also look at the communities and see like what are the questions that are coming in, if there are any unanswered questions, and we try to answer their questions. But please take advantage of the free no limits student edition and try to use it for your projects. And also, there is a very nice book where co-authored by Dr. C.G. Reddy. Here you can see lots of different types of examples for different types of antennas. Okay. So you can go through all those different examples, and all those examples in the book are solved with Feko. So you can definitely use this book as a guide to not only learn antennas, but also at the same time learn how to use Feko for antenna design and analysis. With that, that concludes the live demonstration of Feko for antennas, antenna arrays, design and optimization. If there are any other questions, I'll be happy to answer.
I don't think there are any questions left in the chat window here. But just maybe a remark that any of you have questions and things like that, as Gopi mentioned, you can go to Altair forum where these questions can be asked. But also, as Gopi mentioned, the email address, reach out to us and we'll be happy to help.
Thank you very much. I mean, very detailed information and very insightful. Thank you very much, Gopi and Dr. Seji. I
My
guess, as usual, I mean, we're happy to have you, and maybe we can have more like webinar like this next year. And happy holiday, everyone.